So we've been looking at cumulative distribution functions and probability density functions of a single random variable. We can actually extend these ideas to when we need to work with more than one random variable. So this introduces the concept of joint densities and joint distribution functions. And this situation could arise, for example, I guess the simplest thing to think of is maybe you're selecting a person at random and you're writing down, their height and their weight. So in that case, the numbers that you're writing down, height and weight, those are both random numbers. One experiment resulted in 2 random numbers. Or maybe instead of rolling 8 dice, you roll 2 dice. So instead of writing down just a single number, 1, 2, 3, 4, 5, or 6, you write down 2 random numbers. You write down the first number, you write down the second number. So these and other examples are very easy to come up with, and it makes us realize that when we perform experiments, we're not always going to get just a random number, but we might get 2 or many random numbers. And actually, while we're going to stick with just 2 random variables right here, in general, we would extend this to be working with n random variables, so x, y, z, etc. Or in general, the random variables x1, x2, x3, ... x to the n. But for now, let's just stick with 2 random variables, and let's talk about the joint density of the random variables x and y. So the joint cumulative distribution function, it's now a function of 2 variables, x and y, and this function tells us the probability that the random variable x is less than or equal to little x, and the random variable y is less than or equal to little y. So we call this a joint CDF because it looks kind of like the CDF we were dealing with earlier in that it tells us the probability that a random variable is less than or equal to something, but it's joint because it tells us the probability that one random variable is less than something and the other random variable is less than or equal to something. This is very much analogous to our joint event that we were working with before, the probability of A and B, or A intersect B. The probability of these events, you can frame it in this form right here. Given that we have a joint CDF, we can go to the PDF. When working with one random variable, we knew how the PDF and CDF were related. We could get to the PDF just by differentiating the CDF. And it turns out we can actually do something similar here. It's just that since we're dealing with 2-dimensional function, we actually have to take 2 derivatives, and we actually have to take partial derivatives, one with respect to the quantity x and one with respect to the quantity y. In general, if we had another third variable, then that would be the probability of x less than or equal to x, y less than or equal to y, and z less than or equal to z, and down here we would have a third order partial derivative. And you could just extend that indefinitely for as many random variables as you had. Before we go on to the next chart, kind of keep this probability of A intersect B in mind as we go on to the next chart here. We'll look at this concept in just a second in detail. So we can extend this concept of conditional probabilities to continuous random variable density functions. If you look back a ways in the videos and the slides, we had some expressions that talked about conditional events. For instance, what's the probability of B given that A has occurred? And that was actually related to the probability of A intersect B and then just the probability of B itself. Well, we have similar expressions for conditional densities. So right here we have the conditional density of x given y is equal to the joint density of x and y divided by the density of y. So this is what we call a conditional density, and it's a density for a single random variable given that we've made some observation about the random variable y. So think about a use case here might be something like, what is the distribution of weight given someone's height is such and such? So once you fix height, maybe to say 6'4", that would determine what the density function would be for weight. So you might expect there as that height got larger, maybe the distribution for weight also, its mean moved up, because usually taller people on the average tend to weigh more than shorter people. So that's what we mean by this notation here. Given this y quantity, what is the distribution of this x quantity? And just like before, when we were working with conditional events, we have a similar expression here on the right. A conditional quantity is related to a joint quantity divided by the marginal quantity. And you can write it in 2 different ways. Here is a joint or conditional density of x given y. You can also write it as a conditional density of y given x. And then you can use essentially a Bayes rule for probability density functions and write it in this format here. So the expressions that we had before when we were simply considering the probability of events and the probability of conditional events, you can do a similar development and show that these relationships are true. And these relationships are important for us as we study digital communications, because essentially we're going to be doing things like, given that I've sampled my received signal, what's the probability density function of making an error? What's the probability of making an error? So things like that. So conditional densities are very relevant from a decision theory point of view in digital communications. These relationships, these conditional densities, all simplify greatly if we are dealing with independent random variables. So recall what it means for independent random variables. When we're dealing with independent random variables, that means that their joint PDFs actually factor into a product of their marginal PDFs. So when they're independent, we have a lot of simplifications, because instead of a single two-dimensional quantity, we get to work with two one-dimensional quantities. If x and y are independent, one thing that's nice is the conditional probability density functions essentially collapse to just the marginal. Given y, what's the probability density of x? Well, it's just the probability density of x. This says that y has no impact on the density of x. Similarly, if x and y are independent, given something for y, how does that impact the probability density for y? Well, it doesn't. The conditional probability density of y given x is just equal to the probability density of y itself. So when we work with independent random variables, these conditional distributions simplify greatly, and also the joint PDF and CDF expressions simplify greatly. And for the most part, we do have independent random variables when we work in digital communication systems. Most of the time, the things that we're going to be working with in this class are going to be of this form. Given that I transmitted some random bits and I was corrupted by some random noise, what is the PDF of the received signal, for instance? Those are the things that we'll be examining in the weeks to come. Well, because what I transmitted is independent of the noise corrupting it, then x and y are independent. And then we have a very nice result stated down here. We won't prove this. You would prove this in an undergraduate class on random variables, but we'll just state it here, assuming we're familiar with it. When dealing with independent random variables, if I know the density of x and I know the density of y, if they're independent, and if I'm adding them together, the density function for z is just given by their convolution. So unfortunately we have to go back to convolution a little bit here. Everybody hates that. But when we're dealing with independent random variables, computing the density function for z is actually very straightforward. It's just this convolution operation here. And while this operation here is very simple, it's just one random variable added to another, the communication channels that we're going to be investigating actually fall into this model, because we're going to be transmitting signals and we're going to be adding noise to them before we receive them, such that we observe z at the receiver, and z is the random quantity that we have to deal with at the receiver. And this is the quantity we're going to be concerned with digging out the original message and also quantifying performance in terms of probability of making errors. So while this is a very simple model, it is a very relevant model in respect to digital communications.